What factors does the focal length of a lens depend? Let us find out. Okay. Take the same lens that was used in activity 2. Note the average focal length of a lens that was calculated in the activity. Take the convex lens which used in activity 2 means in previous activity we discussed what is that ray diagrams, draw the ray diagrams for the image formation by lenses we discussed, and we got different, when we change the position of the object we got different types of images, no. So with the help of convex lens, when we change the position of the object we will get a different image distance, then object distance and image distance also changed, that we discussed in previous activity, no. That means in ninth day, day 9th, in that we discussed what is that image formation by different lenses. Means here when we change the position of a object, then image position also changing with different types of images we discussed, so in that we use convex lens, same convex lens we have to use here. Okay, take the same lens that was used in activity 2. Note the average focal length of a lens that was calculated in the activity. So means in that we change the position of an object and we calculate the object distance value, and when we change the object's position, then image position also changed, means image distance value also we notice, means in written we are written in the table object distance, image distance, means we change the position of an object, means when we place the object in front of a convex lens we change the position of an object, then image distance also changing. Okay, that image distance and object distance value we noted, and from that we find out the focal length or not. Yes, we find out. Okay, so note the average focal length of a lens that was calculated in that activity. Okay, now take a cylindrical vessel such as glass tumbler. Okay, take a cylindrical vessel such as glass tumbler. Its height must be much greater than the focal length of a lens. Now we should take one cylindrical glass tumbler. Its height must be greater than the focal length of a lens, means the height of a cylindrical tumbler will be greater than the focal length of a lens. Okay, its height must be much greater than the focal length of a lens. Okay, so take a cylindrical vessel such as a glass tumbler. Its height must be much greater than the focal length of a lens. We require the vessel which has a length depth nearly equal to 4 times of the focal length of a lens. Okay, here we have to take the vessel, okay, which has length means depth that nearly equal to 4 times of a focal length. Okay, we require a vessel which has a length or depth nearly equal to 4 times of the focal length of the lens. Next, keep a black stone inside the vessel at its bottom. Okay, now take a black stone, keep the black stone inside the vessel at its bottom. In this figure one stone is there on the bottom, no, like that we should place. Now pour water into the vessel up to a height such that the height of the water level from the top of the stone is greater than its focal length. Okay, now pour water into the vessel. Now pour water into the vessel up to a height such that the height of the water level from the top of the stone is greater than its focal length. Okay, now dip the lens horizontally using a circular lens holder as shown in the figure. So in this figure one hand is there. In the hand he holds something. What is that? The something is nothing but a lens holder. Now pour water into the vessel up to a height such the height of the water level from the top of the stone is greater than the focal length of a lens. Now dip the lens horizontally using a circular lens holder as shown in the figure 20 in the above stone. So in this figure one hand is there. In that hand what is there? One black color structure is there. No, that is nothing but lens holder. Okay, so now dip the lens horizontally using a circular lens holder as shown in the figure 20 above stone. So the distance between the stone and the lens that is equal to or less than the focal length of a lens measured in activity 2. So here we are immersed lens holder. No, you should see that the distance between the lens and the stone, okay, the distance between the stones and the lens that is equal to or less than the focal length of a lens measured in activity 2. In activity 2, from object distance and image distance we measure the focal length, no. So here the distance between the stone and the lens that should be equal or less than the focal length of a lens measured in activity 2. Okay, now look at the stone through the lens. Now look at the stone through the lens. Can you see the image of the stone? If yes or not, why? Give reason. You can see the image of the stone if the distance between the lens and the stone is less than the focal length of a lens in air. Okay, so here we can see the image of the stone if the distance between the lens and stone is less than the focal length of a lens in air. Okay, so here we can see the image of the stone. The distance between the lens and the stone is less than the focal length of a lens in air. So now increase the distance between the lens and stone until you cannot see the image of a stone. So you can see the image of the stone in the distance between the lens and the stone is less than the focal length of a lens in air. And now increase the distance between the lens and the stone until you cannot see the image of the stone. Now increase the distance between the lens and the stone until you cannot see the image of a stone. Okay, first we are seeing the image of the stone. The distance between the lens and the stone is less than the focal length of a lens in air. Now increase the distance between the lens and stone until you cannot see the image of the stone, means move upside lens holder. Okay, means increase the distance between the stone and the lens. Still you cannot see the image of a stone. What do you conclude from this activity? Does the focal length of a lens depend on surrounding medium? Here you have dipped the lens to a certain height which is greater than the focal length of a lens in air, but you can see the image. Okay, when the lens is raised further, you could not see the image. This shows that the focal length of a lens is increased in water. So thus we conclude that the focal length of a lens depending on the surrounding medium in which it is kept. So means here is nothing but, here we took one cylindrical transparent vessel. Its height is 4 times greater than the focal length. Now we kept one black stone at the bottom of the stone. So now we place the black stone at the bottom of the cylindrical tumbler. Now we pour water. Okay, and now we place the black stone at the bottom of the cylindrical transparent vessel. Now we poured water into the vessel up to a height such the height of the water level from the top of the stone is greater than the focal length of a lens. Now we place the lens holder. Okay, now we dip the lens horizontally by using a lens holder in that figure. So set the distance between the stones and the lens that is equal or less than focal length of a lens measured in activity, and try to see the image of a stone. Okay, you can see the image of a stone if the distance between the lens and the stone is less than the focal length of a lens. Now increase the distance between the lens and the stone until you cannot see the image. Then what happened? So here does the focal length of a lens is depending on surrounding medium? So you have dipped the lens to a certain height which is greater than the focal length of a lens in air, but you can see the image. So here when we increase the distance, first the distance between the lens holder and stone is less than or equal to focal length. That time we can see the image. Now we increase the distance between the stone. Okay, now we increase the distance between the stone and lens holder. So that time also we can see the image. Okay, you have dipped the lens to a certain height which is greater than the focal length of a lens in open air. So the distance between the lens holder and the stone is greater than the focal length of a lens. Then we can see the image. Okay, but when the lens is raised further you cannot see the image, means more than this focal length. If we increase the height of the lens, then we cannot see the image. So here this activity shows that the focal length of a lens is increased in the water, that we conclude that the focal length of a lens is depending on the surrounding medium which it is. Now we will discuss one problem. In previous activity we discussed lens maker formula, no? So from that lens maker formula also he will ask some problems. Now we will discuss one problem related to this lens maker formula. Okay, first I will explain about the question. What is the focal length of a double concave lens kept in air with two spherical surfaces of radii? R1 is equals to 30 and R2 is equals to 60 centimeters, and take the refractive index of a lens is n equal to 1.5. So here we have to discuss now what is the focal length of a double concave lens. It is kept in air and with two spherical surfaces. Its radii is R1 30 centimeter and R2 is equals to 60 centimeters. Take the refractive index of a lens as n equal to 1.5. Okay, once you observe the figure, okay, it is biconcave lens. So in the biconcave lens, rays are traveling parallel to principal axis. So then that all the rays are diverging after falling on the biconcave lens, that all the rays are diverged. If we extend the diverged rays backward, that appears to be come one point. If we extend the refracted rays, okay, on biconcave lens, all the rays are traveling parallel to principal axis, falls on the lens and diverging. Okay, extend the divergent rays backward, that appears to be convergent one point, that is focus. So from the focus, that rays are appears to be coming. So that we discussed in the activity. What is that in ray diagrams? Find the focal length of a lens. We discussed, no? The rays traveling in figure A to A and A to B. Once you observe the figure A to B, all the rays are traveling parallel to principal axis after falling on the lens. After falling on the biconcave lens, it will diverge. So if we extend the refracted rays backward, that appears to be convergent one point, that is focus. And figure 8 we discussed all the rays are traveling parallel to principal axis after falling on the biconvex lens, that appears to be convergent one point. That point is real focus, that is F1. After that F1, C1 is there. Okay, and biconvex lens left side F2, C2 is there. Yes or no? At the same time in figure A to B, the parallel rays fall on the biconcave lens and that is diverging. If we extend the divergence, appears to be intersect at one point. That point is focus. Okay, that is F1. And F2, which side will be there? Convex biconcave lens, right side F2 will be there. So in figure 8a, all the rays are traveling parallel to principal axis, converge at one point, that is focus F1. After the F1, C1 is there. So this F1, C1, R1 is positive in this situation. Why? Because we are measuring the direction of incident light. Okay, and F2, C2, R2 are negative in the case of this biconvex lens that you observe in figure 8a. And in figure A to B, all the rays are traveling parallel to principal axis, fall on the biconcave lens and that is diverging. Okay, so here if you extend the divergent rays backward, appears to be that coming from one point, focus. Okay, so focus is nothing but the rays are appears to be converge at one point, or the rays are appears to be emanate one point, that is focus. Okay, so in a biconvex lens, F1, C1, R1 are positive, F2, C2, R2 are negative. In biconcave lens, F1, C1, okay, and U next to R1, these all are negative. Okay, in concave lens, F is negative, V is U is negative, R is negative. In convex lens, F is positive, okay, and V is positive, U is negative, R is positive. Okay, in biconcave lens, R1, in biconcave lens, R1 is negative, R2 is positive. In biconvex lens, R1 is positive, R2 is negative. Remember these terms, okay? We have one problem. What is the focal length of a double concave lens kept in air with two spherical surfaces of radii? R1 is equals 30 cm and R2 is equals 60 cm. And take the refractive index as n is equals to 1 minus 1.5. Okay, so here two radii of curvatures are given, R1, R2. Okay, and refractive index of a medium is given. What is that? N is equals to 1.5. Refractive index of a lens is given, that is n is equals to 1.5. And we should find out the focal length of a double concave lens. Yes or no? F we have to find out. We have R1, radii of curvature R1 is equal to 30 cm and radii of curvature R2 is equal to 60 cm is there, and the refractive index of a lens is there, that is n is equal to 1.5. And what is F? F we have value, we have to find out. What is the formula related to this all? 1 by F is equals to n minus 1 n minus 1 into 1 by R1 minus 1 by R2. N is equals to 1.5 is there, no? That substitute in the place of n. 1 by F is equals to 1.5 minus 1. Okay, open bracket. R1 is equals to 30, no? So R1 means it is which lens? Biconcave lens. For biconcave lens, R1 is negative. So that's why we have to write here 1 by minus 30. Okay. Next, minus 1 by 6. Okay, 1 by R2. R2 is equals to what? 60. This 60 is positive, no? R2 is positive. That's why plus 60 we have to take. Okay, 1 by 60. 1 by 60 we are written. Okay, and finally what will come? 1 by F is equals to 1.5 minus 1. Open bracket, 1 by minus 30. Minus 30 why we are written? It is biconcave lens. In biconcave lens, R1 is equals to negative. That's why minus 30 we are written. Next, minus symbol. 1 by R2 means 1 by 60. Okay, so 1 by F is equals to 1.5 minus 1 means 0.5. Okay. Next, take LCM. Like in first chapter we discussed some problems related to mirror formula, like that. So take 30 and 60 LCM. 30, 60. Then what will come? 60 will come. So minus 1 by 30 into 60 minus 1 by 60 into 60. Okay. Cut 32 are 60, 61 are 60. Then what will come? 1 by F equal to 0.5. Next, minus 2, minus 1 into 2, minus 2. Next to minus 1 divided by 60. Then 1 by F equal to 0.5. Open bracket, minus 2, next minus 1. What will come? Minus 3. Minus 3 by 60. Okay. Then 1 by F equal to 0.5. We can write 1 by 2 also, no? That's why we are written here 1 by 2. 1 by 2 equal to minus 3 by 60. Okay. Minus 3 into 1, minus 3. 62 is 120. Okay. So 1 by F equal to minus 3 by 120. Then cut it. What will come? How many times it will go? 40 times it will go. No. Then 1 by F is equals to what will come? Minus 1 by 40. So this 1 by F is equals to minus 1 by 40. Now that what you can write? F is equals to minus 40. So then focal length is equals to how much? Minus 40. So what is the focal length of this biconcave lens? Minus 40 centimeter. Okay. Here the minus indicates that the lens is divergent. Means this biconcave lens is called as diverging lens. Okay na? Once you observe the figure A and B means focal length of a lens we discussed in that topic. Once you observe the figure A and B, in that first biconvex lens is there. All the rays are traveling parallel to principal axis, fall on the lens, converge at one point, focus. That is F1. Means F1, C1 this side is there. It means in the direction of incident light is there. No, that's why these are positive. And F2, C2 that side are there. That are negative. So for biconvex lens, R2 is negative and R1 is positive. Next, same in figure A to B. All the rays are traveling parallel to principal axis, fall on the lens and diverging. Okay. Extend the divergence backward, that is converted one point, that is focus. Okay. So this is focus, no? So see here F1 is there. After that C1 is there. And biconcave lens right side F2, C2 is there. Yes or no? Yes, it is there. Okay. So means R1 is this side only there, no? So this R1 is negative. R2 is right side is there, that is positive. Okay. And in this focal length is negative or not? Yes, focal length is negative. Why? Because we are measuring opposite to incident ray. No, we should follow these rules compulsory. We are measuring opposite to incident ray. That's why focal length is negative. No, that's why in final answer f is equals to what came? F is equals to minus 40 is came. Okay, understood? Okay, so like this we can do the problem, and we have the problems related to lens formula also. 1 by f is equals to 1 by v minus u, like that also problems will be there. Same these problems also relate to the means object distance, image distance values he will give. From that we can find out the focal length value. So like that also we can do, and he will give the same problems. Here we discussed the problem related to concave lens. No, he will give the same problem related to convex lens, and follow the sign convention, substitute the value and find out the focal length. We can do easily. Now we will discuss